Hi everyone, welcome to this series of presentation on inferential statistics. In this video, we'll talk about one of the technique called ANOVA, analysis of variance, which is essentially an extension of t-test. Imagine you are comparing the effect of fertilizers on plant growth, and ANOVA actually is used in such situations where you have groups of data and we are analyzing whether the effect of, for example, fertilizers is there on the plant growth or not. So ANOVA actually works by comparing the variation between the groups and also within the groups. So if the fertilizer has a larger effect or a big effect, the variation between the group will be larger. So this is the basis on which the ANOVA works, and I'm going to show you how stepwise how each of the step is performed in ANOVA. I'll also show you the SciPy library by which you can perform ANOVA with just one or two lines. So let's get started. So some of the prerequisites, knowledge about you know a beginner level knowledge about Python and also statistics like probability distribution functions and cumulative density functions, probability density functions, and a p-value would be really handy in understanding ANOVA. So essentially, ANOVA is a variance-based technique, and it is used to compare the means among the three or more groups. Like in the previous lecture, we covered t-test, and t-test was limited to two groups. Now here, if you have a situation to compare the means among three or more groups, then in that case, we choose ANOVA. And this allows us to look at the variability within the group and also between the group or across the group. So this is the basis on which ANOVA actually works. So there are two types of or other variations of ANOVA, one way and two way. So let's look at what is one way ANOVA. So one way ANOVA is about one categorical variable or factor, and that categorical variable can have multiple groups. So for example, if you have a treatment group for a single factor, let's say diet type, and you could be exposing your patients to different diet type like A, B, C, D, and for each of the categories you have measurements, then we can perform ANOVA, and that ANOVA is called one-way ANOVA. So basically one categorical variable. Two-way ANOVA has two categorical variables. For example, if you're analyzing diet type and exercise level, on the measurement called weight loss. So both of these variables are impacting or playing a role in weight loss or not. So it's called two-way ANOVA. So variability is the basis on which ANOVA functions. So let's understand what is variability and how this is measured. So the idea of a variance is the same idea of variance that we studied in the basic statistics is also used here. Now, variability is measured in two ways. One is within the group itself, like each of the group, and also variability across the group. For example, exam score in different teaching methods. Let's say we have a different teaching method, and methods are A, B, C, and then you would like to see the effect of those teaching methods by recording the exam score, and then we can perform the ANOVA test to see if there are significant variation because of the teaching method. So variability within the group represents the variation in the exam score within each of the group here. So it's like a categorical variable diet type A, B, C. Then we are looking at for A and B and C, what is the variability within the group. So in group A, the student may have diverse study habits, different levels of understanding or IQ or EQ, and varying degrees of engagement, and that causes variability within a group. So with the variability within the group, how do we measure the same concept of variance? So this is my value, and that's the mean of that series. Subtract it and square, and do that for all the observations you have in the group, and divide by number of samples. So aggregation. So that gives you the variability within each of the group. So basically here we are measuring how much each individual data point is away from the mean of that group or respective group. So how do we do so? Here compute the mean of a group, each of the group, and then calculate the difference or deviation of a data point from the mean. Square the differences and add them up. All of these differences, you simply add them up. And then after that, we average the squared sum, and that gives you the variance within a particular group. For example, here, group A, group B, group C, and then I can calculate the mean for each of the group and calculate the overall mean. This overall mean will be used in the other part of the variability, which is across, not in this. So then we subtract the mean from each of the data point. For each of the group, we take the respective mean and subtract from the data points. And that gives me a total variability within the group. Let's say group A, group B, and group C, and we add them together. So that gives you a total variability within the group. So intuition behind the variability within the group, it measures the spread or deviation or a scatter of individual data points in their respective groups. Intuitively, this is a measure of diversity or heterogeneity across the observations. Now, the second part is variability between the groups, or rather across the group. So this is calculated using the overall mean. So now what we're going to do, we'll find out the overall mean like we already did in the previous step, and that value will be used to compute the variability between the groups. So the step is pretty much the same, just that now we are looking at all the groups together and find out the overall mean. So the worked out example, the same group A, group B, group C, and this is the mean of the group A, B, C. And then we find out the overall mean across or for all the groups here. This is my overall mean. So the variability will be 87 minus 85, 80 minus 85, 90 minus 85 square. And that gives me the variability between the groups. So you substitute all those values and you get the variability between the groups. Now, what's the intuition behind the variability between the group here? This gives an extent to which the means of different group is deviating from each other. So you have a common mean across all the groups, and then you're looking at individual means and then see how much variation or deviation exists. So intuitively measure the influence of the treatment, let's say the fertilizers or any teaching method. So what is the impact of that treatment on the data overall? So test statistic for ANOVA is always going to be starting from zero because of the measurement that we are using, which is variance. And F distribution is the distribution that we use here, and this is used to compute the critical value and also the p-value for final conclusion. And this is not going to be negative. This is only for non-negative values. So F distribution is positively skewed and starts from zero, extending to positive infinity. So like the t-test, ANOVA, which is essentially an extension of t-test, this also has some assumptions that we have to ensure. The assumptions are also similar to t-test, One is the normality of the data, and then the homogeneity of the variances, which is also related or relevant for t-test. Independence of data is also the same condition that holds true for t-test as well. So we need to make sure the assumptions are, meeting before we, perform ANOVA. So there are some variants of ANOVA. So one-way ANOVA, two-way ANOVA, we already discussed, and there is multivariate analysis as well, which is called MANOVA. MANOVA is an extension of ANOVA, slightly complicated and sophisticated. Here, more than two dependent variables can be tested. So let's take a look at some Python code demo, how ANOVA can be performed. Let's take a look at a simple demo how one-way ANOVA is actually performed. So I'm taking a data, something like this, a categorical variable, which is called strength, and the value would be strength 1, strength 2, strength 3, strength 4. So it means there's a column, one categorical column called, x0, and underneath you have a value strength 1, and similarly 2 and 3 and 4, and these are the measurements that you have for each of the this strengths here. So this is what this table actually means, and this is called one-way ANOVA. So let's perform one-way ANOVA here with this simple example. So the hypothesis is there is no difference between the mean of those groups. Like, strength 1 has the same mean as strength 2 and 3 and 4. So that's my null hypothesis. The alternate hypothesis will be just the that there is difference. So we cannot say which one is different to which one, but we will say that there exists some difference, and that's called alternate hypothesis. So let's look at some SciPy stats is the package that we use to perform ANOVA. And the data, these are my data, uh, so these are my different groups here. And one-way ANOVA, you pass all the groups. So in this case, I have three groups. You could have more than 3 groups, 4, 5, 6 groups. And it's called one-way ANOVA because this is actually one variable which has different distinct values. Distinct values are, for example, control 1, control or 2 and 3 and something like that. So, and then after performing the ANOVA, you're going to get the F value, which is actually same as or similar to what we saw in t-test statistics. P value is a probability value. So notice here the p value is 0.15, which is actually lesser than 0.05. Then we can reject the null hypothesis. But in this case, this is not so. Or this is so. So this is lesser than 0.05. So reject the null hypothesis. So when we reject the null hypothesis, it means the means of those groups are not similar. So that's the conclusion here. So likewise, you can take more data and do the one-way ANOVA and visualizing the critical values and the rejection region. We can do a plot again. So let's say we look at the values for F value or F statistic ranges from 0 to some number. I'm taking 0 to 5. And then for each of the value within this X, so I've divided the range of 0 and 5 into 1,000 different numbers or equidistant numbers. And for each of the number, I'm going to generate the PDF or probability density function and using a package called stats. Now I have the data point, which is F value and corresponding PDF. So we're just going to simply plot it. And before plotting, we also have the critical value and use the critical value here as the area to say this is my rejection region. My test statistic is 0.22, which is not in the rejection region. That means you are not going to be able to reject the null hypothesis. So this is how we perform one-way ANOVA, and we do visualization using a simple Python plot. Let's take a look at another example for two-way ANOVA. And here I'll be using then a variable which has two different variables here, A and B, and then we have a value. So in this case, I'm going to use stats model package, and let's generate some dummy data. So we have this column A and B, and within A we have distinct values, and B also having distinct values. These distinct values correspond to groups within A and B. So the two-way ANOVA is essentially you're saying that the value from A and B, so both the columns A and B, and also we're going to use the interaction terms for A and B. So you need to set up that equation for the stats model OLS package, and once you do, it's going to run um, the ANOVA, and then the results are given to us. In this result, you need to look at the p-value here. So essentially, alpha is 0.05. The p-value here, you need to look at the probability value, essentially this column. If that value is lesser than 0.05, we are going to reject the null hypothesis. So here in this case is not so. So we are not going to be able to reject for even B. Let's see for the column B, we are not able to reject it. Even for the interaction term, we are not able to reject it. And like in the one way, so we can generate here also the distribution and show the critical value and the rejection region. So in this case, our F statistic is outside of the rejection region. So we are not able to reject the null hypothesis. So this is how one-way ANOVA and two-way ANOVA are performed. I hope you found it easy. Let's move to the slides now. Okay, so that was the demo on ANOVA using Python and SciPy package. Now, just like in t-test, we talked about the cases where the data is not normally distributed and also is not meeting other assumptions like homogeneity of variances. If that is so, then we cannot use ANOVA here. So the alternative to ANOVA then is Kruskal-Wallis test. This is a non-parametric method of testing whether these samples originate from the same distribution. That means it has the same similar variances. It is used when the assumptions of one-way ANOVA are not met. Essentially, it's similar to Mann-Whitney U-test that we saw in the previous lecture as an alternative to the standard t-test. So this is similar to that, and it's an extension of Mann-Whitney U-test. So when we have more than two groups here, the assumptions here, the before you perform the Kruskal-Wallis, here is that the sample must be independent and data that you can use either ordinal data or you can use continuous data, and it should have similar shape distribution. So when to use Kruskal? Whenever the conditions of normality and the homogeneity are violated, you have to consider some non-parametric inferential technique. And when the data is ordinal data as well, you can use with the Kruskal-Wallis. For standard ANOVA, we cannot use ordinal data, but here with Kruskal-Wallis, we can consider even the ordinal data and non-normally distributed data. So essentially about comparing the means of three or more independent groups. Why three or more, not means, sorry, medians. And the reason is median because this is non-parametric type of inferential technique, and quite popular in the medical research and agriculture and psychology and education. A lot of use cases um, you have implemented the non-parametric version of ANOVA. So that's it in the topic. In this topic, we'll see you in the next lecture. Thank you all for watching.